Types of spectra. Refraction through a prism. To show that the angle of deviation delta equals I1 plus I2 minus A. According to the equation 1, we know that delta equals I1 plus I2 minus R1 plus R2. But according to equation 4, R1 plus R2 equals A. Hence, absorption's spectrum. Dispersion of light. Deviation without dispersion. The angular dispersion produced by the crown glass prism is pure and impure spectrum. Spectrometer.
Wrong. 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 Right. Wrong. 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 Right.
Myopia or short-sightedness. In the normal eye, the far point is at infinity. The rays coming from the distant object at infinity get focused on the retina. In turn, the retina convey the message to the brain via the optic nerves. Causes of defect in the defective eye. The defect arises due to either the length of the eyeball is elongated, that is, becomes longer than normal, or the focal length of the eye lens has decreased. Due to either or both the causes, the eye is not able to focus the rays from a distant object at the retina. Focusing is there at a point O in front of the retina. The image formed on the retina is blurred. The defective eye is, however, able to focus the object up to its far point. Correction of defect. We A simple microscope. A simple microscope is a convex lens of small focal length placed at a distance less than the focal length of astronomical telescope. The astronomical telescope when the image of distant object is formed at D. To trace the path of the rays through the lenses, consider the rays coming from the top of a distant object. As the object is far off, the rays from its top fall upon the lens as a parallel beam inclined to the
As we have learnt earlier, positively charged particles are fixed in place, whereas the negatively charged particles, called electrons, are free to move around. A metal typically has an equal amount of positively and negatively charged particles, making the metal as a whole electrically neutral. If we apply a force trying extra electrons into this metal plate, we will not be successful because particles with the same charge repel one another. If extra electrons accumulate inside the metal plate, they will repel each other and repel any of the new electrons trying to enter. Therefore, even if we apply a force, the metal will remain electrically neutral. Now let us consider a new scenario where there is another metal plate close to the one shown. As electrons accumulate in the first plate. They will repel the electrons in the second metal plate. The positively charged particles left behind in the second plate will exert an attractive force on the negatively charged particles in the
The sonometer is an apparatus used to study the transverse vibrations of stretched strings. It is a hollow wooden rectangular box with two bridges and a pulley at one end. A string wire is attached to one end, run over the bridges and pulley and attached to a weight hanger hanging below the pulley. Here, we are using the sonometer to determine the frequency of alternating current. Theory. When the length L of the sonometer wire vibrates with maximum amplitude, the frequency of the applied AC is equal to the natural frequency of the wire. Therefore, frequency of AC nu is equal to 1 by 2L into root of T by M, where T is equal to mg, the tension of the wire, and m is the linear density of the wire. Therefore, nu is equal to 1 by 2L into root of mg by m, that is equal to 1 by 2 into root of g by m into root of m by L square. M by L square is a constant. If r is the radius of the wire and rho is the density of its material, m is equal to pi r square rho. Materials required: sonometer, step-down transformer, horseshoe magnet, weight hanger, set of slotted weights, paper rider, bridges, screw gauge. Procedure: place the sonometer on the table. Attach a weight hanger at the free end of the string which passes over the pulley. Stretch the wire by loading a suitable maximum mass on the weight hanger. The sonometer wire is connected to the secondary of the step-down transformer. The horseshoe magnet is mounted at the middle of the sonometer bed so as to produce a magnetic field perpendicular to the wire. The opposite poles of the magnet must face each other. The bridges are placed on either side of the magnet at equal distance from the magnet and are close to each other. A light paper rider is placed on the wire between the bridges of the sonometer. The AC supply is switched on. The wire begins to vibrate. The length of the wire between the two bridges is adjusted till the wire vibrates with maximum amplitude. At this stage, the paper rider placed on the wire falls, which shows the condition of resonance.
Here we are going to demonstrate at least one reading for the first experiment, and the experiment name, as you already know, It is determination of focal length of a biconvex lens. So as you can see, this is a biconvex lens bulging from the center, okay, and tapering at the ends, okay. So this is the biconvex lens that we will take. The first step was to measure the rough focal length. So as you can see, this is a screen over here, okay, and I have put a scale, a ruler over here to measure the rough focal length. Now how are we going to measure the rough focal length? I will hold this lens in front of the screen. As you can see, when I am moving my hand back and forth, so what is happening is the window along with the other objects that you can see the image. You can see here is the image that is getting formed. So this image is blurred right now. We are going to try to get a position of a clear image. So let's say, for example, somewhere here, you see this is a clear window upside down. As you expect from a biconvex lens, the image is inverted, okay. So the window is looking upside down and you can see some trees, leaves also, okay. So if I move the lens forward, it is becoming hazy, as you can see, and now I'm going to bring it back. So you see around this position we are getting a clear image, okay. So I'm going to take this down just for measurement. You can see on the scale it is coming to around 10 centimeter, okay. This distance from the screen up to the position where the lens is there, this is coming out screw to take the pin up and down, okay. Similarly over here you can see, you release the screw and then lens position. You can see there is a white mark here also. The lens position is set at 30 centimeter. What this means is, from the object up to the lens, this distance, as you already know, if you have studied properly, this is the object distance u, okay. So u value we are fixing. Based on this fixed u value, we will calculate, we will try to find out what is the v value. V value means the image distance, okay. So right now the first thing that we have done is we have fixed u as 30 centimeters. So in the observation table, the first column wherever you have u, you will write u as 30 centimeter, okay. Now let us come to the image side. You can see the inverted image of this object. Now you can see that if we will zoom a little more, you see, yes, now right now we have not fixed the position. What I want to show you is this, though obviously is the image pin right in front of our eyes. The image that I am talking about is, you can see this image. It is the image of that object pin which is lying on that side. With the video. Okay, so first of all I'm going to show you how to set this image pin so that we get this inverted position. Okay, so right now you can see when I'm moving my head, you will see that these two things are not moving together, they are getting separate. Okay.